Right. Good afternoon. I'm Tristan from computer science. So my research interest is mostly to build foundations for AI. Although I have been collaborating with a lot of domain people, especially from physical science and medical school. So I think today I'm mostly on the second part of that. So when we talk about inverse modeling, actually I recognize that different domains are using very different terms. They are all inverse modeling, but people just try to use different terms. It could be inverse problem reconstruction. This is used in particle physics, for example, or computer vision. Data simulation, this is used in, let's say, climate science, right? Inverse design, inverse control, conditional generation, for example, in material science nowadays. So the underlying mathematical problem is that we have some measurement, which is observed from some physical process. F is what we call the physical model or the Ford model. And we're trying to recover the object interest X. And traditionally, the people approach this problem by solving some optimization formulation of the problem. Typically, they have two kind of terms. The first kind of terms they call data fitting, where you basically try to make sure that whatever you estimate kind of agree with your measurement, to at least to some extent. And normally, that itself is not enough to give you, reasonable estimation. And normally people need to encode some extra knowledge that you already know about the object that's encoded in the regularization term. So if we look at what the machine learning community now is doing for inverse modeling, most of the research is done for linear problems uh, with without physical constraints. And also normally the Ford model is explicit. What I mean is that you have a nice, very nice mathematical closed form for the F. But if I look at the physical applications, the problem we typically have is that the F, the Ford model is nonlinear. And actually often what we encounter is that the X and Y are related by some PDEs. Okay, and this is especially true for physical science. So you have that kind of physical constraints that need to be modeled here. And also that also means that I don't have an aspect form for F that's implicit. So that's the discrepancy between what's happening in the mainstream machine learning research for inverse modeling and what's actually happening in physical science. That's what I see so far. Um, Now, there are many, many ideas using machine learning to try to solve inverse modeling problems. Today, I'm especially going to highlight one of them, which I think is very, very interesting and also very, very practical. It's called a plug-in kind of method. And also here, when I talk about generative AI, I'm taking a more narrow sense of that. What I mean is that I'm really talking about a generative AI with deep generative models. Okay, because nowadays some people when they say generative AI, they are talking about everything about AI, but I'm using a narrow sense where there must be some deep generative models. Uh, so this plugin approach looks like this from high level that you have a large scale object on the data set. Let's say I collect 1 million natural images, depending on application field, of course. You can collect 1 million particle events for particle physics, for example. And then you try to model the distribution via deep generative models. Again, there are many choices, but nowadays it's super, super popular that people use diffusion models or something that's more general called flow matching models and also the stochastic interpolates. All of these are very similar mathematically. And we just view the whole generation process as a function. Okay, for example, the diffusion process, we start from some random noise, and the whole process, end of the day, are going to generate something meaningful to you, right? We just view this whole thing as a function that's mapping the random noise to the object interest. And then we just plug this into the traditional formulation. Remember last slide I showed an optimization formulation. We just plug that into this. And so you end up with the optimization problem. So the advantage of this kind of approach is that, okay, so you are still using a physical process. So we are still using physical knowledge. And you are using data-driven priors also, which is the model, which is what a generative model provides to you. Okay. So recently we have done quite a number of works really in this line. One of the work we published in News 24 is where you can train a domain-specific models. So when I say domain-specific, I mean, for example, you are interested in reconstruct human faces. Then I take a human face data set and just train a deep generative model to model that. Or you are interested in particle physics, or for certain kind of particles, you train a deep generative model for that. The second work we are working on now, is that we recognize that many domains now, they have some large enough generative models. For example, especially image domain, we have stable diffusion model that probably is trained on 10 billion images. And these models are powerful enough, you can imagine that they can model almost all kinds of images. Okay, so we call this foundation deep generative models. It sounds a little bit weird, but you get what I mean. You can replace this by universal. Okay. So when you move to this kind of deep generative priors, actually something striking happens is because you think these models are more powerful, right? But actually, if you use this to solve inverse problem, these models actually become very weak. Why they are becoming very weak? Well, the reason is simple, because these models are powerful, generate diverse kind of objects, but they also at the same time, because they are not specific, they provide less constraints for you, right? Because in solving inverse problem, you need strong constraints that deep generative model can provide for you. So recently we come up with how to actually bridge the gap. Because people really like to use this kind of available off-the-shelf priors, but they are very weak. So this is what we are trying to do now, basically, how to strengthen the prior so that you can solve practical problem, basically any kind of problem related to imaging. All right, so that's about how to use inverse problem, how to use generative models, especially the recent diffusion models to solve inverse problem. Another thing I want to quickly highlight is a computational tool we are building over the years is that we recognize there are so many problems. For example, the inverse problem formulation I talked about, often they come with hard constraints. And nowadays, the way that people handle hard constraints typically turn that into soft parallelization, but that typically still use something that's physically not meaningful, right? So we are developing this kind of computational framework and also the numerical solvers to handle hard constraints with deep learning models. And also, we actually recently have updated the software so that it's actually compatible with the most recent version of PyTorch. So if you have any computational problem where we come with hard physical constraints, you are welcome to talk to me and try this out. Thank you very much. Yeah.
So diffusion models are great for imagery, but imagery has this nice smoothness property, right? Nearby things smoothly. We love them as spatial autocorrelation in my old field. But there are other data sets which are geometric, right? If you look at the CAD drawings of buildings, right?
Yeah.
And so on, where you don't have that smoothness behavior.
Yeah.
So question is that, do you see diffusion models still applicable to those, or are there other generative models which are better?
Yeah, that's a great question. I think people are trying to generate diffusion models for dealing with discrete kind of data, like the case you described. For example, I think in material generation, people are directly dealing with graphs. So and actually, recently, people are trying to use similar ideas to deal with language generation also, because current large language models are not based on diffusion models. They are based on sequential prediction.
Autoregress.
Yeah. But now people are actually pushing for that using diffusion models also. It seems like there's a real potential that diffusion model can unify every data modality. So
Interesting, but diffusion, it literally means that you will have some smoothness behavior. So how do you kind of stop that and let the discrete behavior flourish?
Yeah, actually I think there are several perspectives about diffusion models. So that's one way of looking at that. Another way of looking at that is basically the noise injection and the denoising process. Because let's say we're dealing with graphs. How do we inject some noise to graph? Well, I can randomly delete some of the nodes, for example, or I randomly protect some of the widths on the edges. And then the reverse process will be like I randomly add in some nodes and I randomly protect the widths. So That's another perspective of looking at diffusion model. So yeah, there are different ways of looking at the same thing basically, and the way to generalize basically depend on different perspectives. Yes.
So, if you go back, certainly the 90s, certainly right. So the whole nonlinear diffusion was used very heavily for edge preserving, like noise reduction.
Yeah.
So that's a case where you can actually worry about the edges and keep the edges while smoothing the smooth ortho images. And we had, I even have some papers on that when Alan Tannenbaum was here, and they found Guillermo Sapiro, these guys, when they were in our department, they were big leaders in that area.
Right.
No, we'll have to leave.
So it might be interesting to sort of examine how that could potentially.
It will be helpful because I think actually I was visiting Japan, so big generation, they tried diffusion, they tried autoregressive, and in their experience, they went back to autoregressive because the lines were not as straight and so on.
Yeah.
But they had to put some pruning, kind of a mild GAN on top of autoregressive. But I will love to read those things.
Yeah.
But I think this idea of keeping the edges, but does that correspond to like having some constraints that you meet and then you diffuse on the other ones? Like in the sense that there's a dichotomy here. Of course, this work obviously is true the AI framework. But what you're saying is, there is some processes we're allowed to do, but something you're not allowed to do. Is there a counterpart here in your own work on constrained modeling, right?
Yeah, I mean, you definitely during the diffusion process, you can add in some rules how you want to diffuse, right? You don't have to allow all possibilities because, like, for example, material discovery, you do have a lot of physical constraints, so you can't allow arbitrary kind of perturbation to your graph, right?
I mean, and Craig, we have papers on recovery using even fourth order.
I see.
Because second order nonlinear diffusion PDEs were used additionally, and we were looking at it for image recovery, which is both sharpening and noising. Then, for example, we discovered certain advantages for using fourth order.
We'll love to read that. Yeah, Guillermo work I had seen at NGA workshop, but he was using second order to remove scratches from the pictures. Thank you.
Just a quick question.
Yes.
Are there any particular types of data sets that could help you kind of do this fixing of the foundation models?
So
what would you look for? What would be ideal?
So currently, the domains that really get this kind of foundational generative models are image, that's very clear. Video, we are starting to see that. Language domain, yes, for sure. I think some physical domains, some physics science domain, they are, at least I saw, DOE have several calls where they encourage, physics domain to start to build foundation models. Although there may be a different kind of foundation models. It may not be a generative kind of foundation model. It may just be like for feature learning, like kind of foundation models. but anyway, I think, more and more domains, more and more, applied domains are going to start to build this kind of foundational generative models. And I think this is becoming more and more realistic, at least for imaging domain, this is now already here. We have a lot of these kind of open source foundation models already.
How about like fluid dynamic simulations? Images almost like a video, but of course video is physically constrained.
Yeah.
Is that some?
Yeah, that's a good question. I think
in college.
Yeah, I think the problem with the current video kind of foundation models is that they are trained on very limited amount of data. Whether we can call it foundational enough, that's still a question mark. So, but they're pushing to that direction.
And there they might mix autoregressive because you can generate frames in sequence, right?
Yes, I think they do have some autoregressive components in that model. Yes. Thank you.